All right, class, welcome into Chapter 9. Congratulations on surviving Chapter 8, if you did. If you didn't, that's all right. We're going to get plenty more combined loading practice in Chapter 9, so don't worry too much. So Chapter 9 talks about stress transformation. In this first set of slides, we're going to talk about plane stress transformation. But before we get into talking about what it is, let's talk about why we want to transform stress. All right, so we have this turbine here. What we'll come to find is that the stresses that we calculated in the combined loading problems and all the previous chapters are only with respect to the coordinate system that we set up. But if we were to look at planes at an angle, we're going to find that the stresses are going to be completely different because of how the equilibrium equations work at different angles. We'll also see, crucially, the maximum stresses don't necessarily just magically match up with our typical arbitrarily defined XYZ axes. For a lot of problems, they'll be at some angle and at some direction, and in 3 dimensions at some plane rotated with respect to our Cartesian coordinate system. So, to best design your systems and choose the materials appropriate to withstand certain loadings, we need to find where and in what direction the maximum stresses occur. So that's the ultimate point of stress analysis. And then beyond that, we're going to talk a little bit about design and some failure analysis, though MAE 343 talks more about the failure analysis of materials, how that relates to our stresses and our transformed stresses. If that doesn't make any sense, this picture shows a little better of what I mean. So we have this concrete block here being bent between 3 different points, one here, and then here. Okay, we call that 3-point bending, very original name. And concrete's well known for not being very good under tension. So what you end up having here is some tensile stresses developing in certain parts of this beam and at certain angles. And by doing some stress transformations that we're going to do in this class, you can find where that's going to occur in your material. So in the first couple sections of Chapter 9, the ones that make up this set of lecture slides, we're going to develop the equations if we were to rotate to any angle, and then we're also going to develop the equations to find the maximum normal and shear stress values and the angles at which they occur. So that's, in the end, what we generally care about for design purposes. But before we get into actually developing those equations, we do need to talk a little more about the background of this general state of stress. Okay, we've talked about this a lot throughout the class. Even on day 1, I think I drew this cube up on the board for you, showing you where we want to get in this class. So you know this cube is basically representing a zoomed in differential element of our material at a point in space. This is what we were starting to get into in Chapter 8. After we found our stresses, we would draw them on our differential element to show how they're acting on our material. And we know that we have all of these different normal and shear stress possibilities when we're working through our problems. Okay, so this general state of stress at a point is characterized by what we say are 6 independent normal and shear stress components. You'll have 3 independent normal stress components and then 3 independent shear stress components. 3 normal stress ones we know are sigma x, sigma y, and sigma z, coming out of your x, y, and z faces. They have opposing stress components on the opposite faces in the negative directions. And then our 3 independent shear stress components are going to be tau xy, that's on our x face in the y direction, tau xz on our x face in the z direction, and then we have tau yz on our y face in the z direction. Our other 3 components, though, are just going to be those letters reversed, And we know, though, from equilibrium that those are going to have to be equal to the stress components that have the same letters in them, but in a different order. So tau yx would be equal to tau xy. So this is on our y face in the x direction. That's why it's just labeled as tau xy. They're not independent of each other. They have to be equal so that this cube is in equilibrium. And then they need to be in opposite directions on adjacent faces, so that they cancel out the moment or rotation that they create on the cube itself. Okay, so that makes up our 6 components of our general state of stress. But this complex state of stress is not often encountered in engineering practice. What we usually have is just this plane stress that we call it, where we have 2 normal stresses, sigma x and sigma y, or it could be in some other plane, doesn't matter. Our axes are arbitrarily defined. But then you only have 1 shear stress. In this case, it would be tau xy, since we're in the xy plane. So this plane stress in 3D looks like this, with sigma x, sigma y, and our 1 shear stress, tau xy, that's in the xy plane. That can be squashed down. If you were to make this 3D element into a 2D looking element, you now just have a square, and your normal stress components coming out of the x face here. So coming out of the x side, but think of it as a 3D face there. Sigma y is your normal stress coming out of the y face, and then again your tau xy. Okay, this is how we'll typically look at our state of stress, is just in a 2D plane, because that's how we simplify a lot of these problems. And now, if we were to take this same element and rotate it, where our x and y axes are now what we call the x prime and y prime axes, we're rotating it through an angle theta to give it a different orientation, then it's going to have new stress components. If we were to take a cut through material and find our normal and shear internal resultants, we would get different values, right? Because we're at a different angle. Well, this change in the angle is going to give us different stresses in the normal and shear directions, just as it gives us different forces in the normal and shear directions. This is a stress transformation. This is the basis for what we're going to do throughout Chapter 9, and it's the final piece of the puzzle for our standard stress analysis in this class. So again, we have our 2D stress element. Now we need to talk about the sign conventions for everything. Right, so our state of plane stress at a point, again, is uniquely represented by these 3 components acting on an element that has a specific orientation at the point. So this is our arbitrary x and y axes that we start out with, and then we rotate it through to our new axes, x prime and y prime. As usual, if we have a normal stress component coming out of a face, again, imagine this as a 3D cube, this normal stress coming out of the face, that's a tensile normal stress, that's going to be a positive one. Same thing goes for in the y direction. Okay, so positive normal stress acts outward from all faces. Now for the shear stress positive sign convention, so over here on our x face in the y direction is our tau xy, and if that's going up here, meaning going in the positive y direction, we're going to consider that a positive tau xy, a positive shear stress. Okay, this is on the positive x face, again, going in the positive y direction. If you look over here, this is going to be the negative x face. That's going in the negative y direction. Those 2 negatives cancel each other out. So that's really a positive shear stress on this face. Same thing up here. This is our tau yx, which is again equal to our tau xy, but in this case, it's on the positive y face going in the positive x direction. That's a positive shear stress. And for our angle, we're following the right-hand rule. So a counterclockwise rotation from x to x prime or y to y prime is a positive angle. All right, now we're going to actually derive some equations that we can use if we already know our 3 components, sigma x, sigma y, and tau xy. We can use these equations to transform those stress components into these transformed axes according to these free body diagrams. So if we section through our plane and rotate our axes like this, so the x-axis gets rotated again to the x prime on the hypotenuse of this right triangle that we just created through our square element, what we end up getting is our normal stress is acting over this differential area, so that's normal stress times delta area, that's our differential area. Same for our shear stress, but on our other sides of the triangle, what we get are that the other two sides of the triangle that's left behind act over the cosine and sine components of our hypotenuse area. Okay, so this area is now larger. These ones are smaller. We have to multiply by cosine of theta for this one and sine of theta for this one. After we draw this free body diagram, we just sum the forces in the x prime and y prime directions to find our new transformed stresses. That is our sigma x prime and our tau x prime y prime from our original sigma x, tau x, y, and sigma y. And we end up with the sigma x prime, sigma y prime, and tau x prime y prime over here. So it looks something like this. It's a lot, right? So here you sum your forces in the x prime direction, going at that angle that was coming out of the hypotenuse of the right triangle. And you have your force component coming out of that hypotenuse. That was the sigma x prime times that delta A. And then you have to get your x components coming from your other two faces with your shear stress and your normal stresses coming out of those other two legs. You can solve for sigma x prime. You get this equation. Use some trig identities, and it simplifies down to this slightly more reasonable equation here. For summing the forces in that y prime direction, in that direction, you can solve for tau x prime y prime in the same kind of way. Simplifies down with some trig identities like this. So that's how you get sigma x prime and tau x prime y prime. But for sigma y prime, you'll see the only difference here is we have change in a plus and a minus here. That's because to get from x prime to y prime, all we're really doing is replacing theta with theta plus 90 degrees because we're rotating our axes a further 90 degrees. So those normal stresses are interrelated in that way. So I'm going to take you through some of these examples, but some of them are probably best if you read through yourself at your own pace and use them to work through your homework problems as well. So in this case, we have our typical XY coordinate system, and we want to find the state of stress at this point, but on another element that's oriented 30 degrees clockwise from the position shown. So all we're doing is taking this, rotating it down 30 degrees, finding the components of the stresses from there. So from our sign convention, we had the negative 80 megapascals in that x direction, because it was compressive. Positive 50, as it's tensile up here and down here. Remember, we have to be in equilibrium, so if we're compressive on the right, we need to be compressive on the left. And then our tau xy follows the sign convention where this guy here on the right side, our tau xy is going in the negative y direction. So this 25 is actually a negative 25. Okay, and then our theta is negative 30. Well, all you have to do is plug these values exactly as you see them into our transformation equations, and you get the answers. Okay, we started out with megapascals. We're going to end up with megapascals here. So you get negative 25.8 megapascals in the x prime direction, and for our tau x prime y prime, you get a negative 68.8 megapascals. So it's going to be going down on the right, and that's exactly what we have here. Now on this slide, though, it shows to find the stress components on plane BC here, which actually, if we go back, would be the y prime direction. We're just going to use an angle of theta equals 60. Instead, what we could do is plug in an angle of negative 30 into the equation we had for sigma y prime back here, and we're going to get the same answer as what we get here when we plug in a positive 60 into our sigma x prime. Remember, x and y, they're arbitrary axes. All that matters is where we're rotating from and where we're rotating to, what we start with and where we're trying to end up. So you get a negative 4.15 megapascals when you plug in all these values here. Same starting values, just a different angle. And that's going to be a compressive normal stress up here on this x prime in this x prime direction. But again, that's what we called our y prime direction on the previous slide. Hopefully that's not too confusing. This is a different kind of way of showing it. But now we get a positive 68.8 megapascals on this face. So that one's going to be going in the positive y prime direction the way we drew it here. Okay, so we got negative on this face, negative over here, but positive on this face, so positive on this face here. So for these example problems, though, we're not going to bother with really cutting through and making the right triangles. We're just going to use our derived general equations for plane stress transformation and plug in our values that were given or that we find from our combined loadings. So these problems end up being mostly just plugging and chugging, but you do have to understand your sign conventions and understand exactly what it's asking for. Now there are some problems on the mastering homework that aren't quite as straightforward in determining what your angle is, but remember, if you cut through a plane, what you're looking to find is the angle that's normal or perpendicular to that hypotenuse of your cross section. In this case, we're just asking you to rotate the square element a clockwise 30 degrees. So go ahead and try out the first part of the Chapter 9 homework, and I'll see you. All right, so you're pretty much capable of doing the first part of the Chapter 9 homework, but I'll see you over at the Chapter 9 worksheet number 1 if you want to go through that first.